Thank you, and a hearty welcome from southern Germany from me as well. And welcome to my talk about hexagonal architecture, and this, which should be the standard for Qt embedded HMIs, but I'll come to that. So over the last 25 years, yeah, you see my gray hair, that's how long I'm working already professionally. So over the last 25 years, I built my fair share, my fair deal of Qt applications. First, I built a couple of desktop applications with Qt, so an IDE for formal verification of ASICs and an IDE for Bluetooth and Zigbee development. They are still around, so they are still used these days. And then 15 years ago, I switched to Qt embedded HMIs. So HMIs written in Qt, running on embedded systems. And there I built, you see one of them, an operator terminal for the Krone forage harvesters, then one for sugar beet harvesters, for metal sheet bending machines, so doing metal origami, and one for medical cleaning robots. And then I did some infotainment systems for cars, obviously, but also for e-bikes, yep, same as cars, and for planes. So what I didn't notice over the 25 years was that I was unknowingly converging towards the hexagonal architecture. And I figured that only out 2 years ago when I found the article from Alistair Cockburn, and it dated back to 2004. So I could have probably saved me a lot of time and dead ends and bloody noses and so reading that article earlier instead of figuring that out myself. But maybe I wouldn't have understood the article in 2004, and so I went my way and arrived at the hexagonal architecture. And in this talk, I will argue that hexagonal architecture should be the de facto standard architecture for embedded HMIs. Not just Qt embedded HMIs, you could also say for HMIs in general, but I limit myself to Qt embedded HMIs. And what are the main characteristics of an architecture? So you see that on the left-hand side. So it should be a good architecture. It should be technically sound. It should be the right architecture, meeting stakeholder needs, and it should be a successful architecture, meaning it delivers value to the customer. So, or to the company who builds the Qt embedded HMI. And well, most of us, me including, start with a big ball of mud architecture, and which is definitely not technically sound. It might meet the stakeholder needs. So if your HMI only has to live, say, for 3 years, you might avoid the big rewrite, which inevitably comes with a big ball of mud. But if your architecture has to last for 15 years, then it won't do. And then it will, so the value you can create will go down exponentially while your technical depth is going up. So what I found pretty quickly was, well, I could use a 3-layer architecture. So with a GUI layer, with a middleware layer, and then some data layer where going to the to databases or going to the machine, so doing the machine communication. And funnily, the hexagonal architecture is actually it's a generalization of the 3-layer architecture. And so let's dive into that. One warning before that. Why is architecture important? Architecture is like an iceberg. Only 1/10 is visible. And the Titanic disaster teaches us what happens when we ignore the other 9/10. And I've seen too many projects who started without an architecture or with the wrong architecture, and then they hit a wall typically after 3 to 5 years, and where they had to re-implement basically everything or large parts of their application. And we are easily talking about a couple of millions of euros or dollars you can sink with that. So it's important to get the architecture right and to find the right architecture. The motivation. So what's the motivation for the hexagonal architecture? It's also called, the official name is ports and adapters architecture. The idea is the same as with USB ports. In modern PCs, laptops, also you only find USB ports. So my MacBook here, well, has 2 USB-C ports and, well, an audio jack on the other side. So I need adapters for everything, but it's the same with my build server under the table. And so you have an adapter from USB, say, to CAN, to RS-232, to UART. You have these wireless LAN dongles or adapters to Ethernet. You have HDMI adapters, whatever, and it's all goes into USB, which is standardized. So if your adapter implements the USB interface correctly, the USB standard correctly, then it will work. And the advantage is, well, you just have one type of interface that's good and not 5 or 10 as 20 years ago. And different companies can build the different adapters. Now let us transfer that idea into software. And here is the hexagonal architecture, ports and adapters architecture. So the PC is now the business logic. And the business logic has, well, not USB ports, but it has ports to different adapters, like a port to the GUI, which serves the models, as in model view controller. A port to the cloud to pass out, say, diagnostic information for remote support, or it allows over-the-air updates and so on. And obviously there's a machine communication, so machine port with a machine adapter, and typically there's a database. So that's a very typical Qt embedded HMI, and I've written enough of them. So the port is an interface between the business logic, which is the inside, which is the small red hexagon, and the adapters on the outside. We have 2 types of, so an adapter is, we have 2 types of adapters actually. So we have the ones like the GUI who use an interface. So the GUI uses the model classes. So as in the model view pattern. So the GUI uses these classes. And then we have the other type of adapters, and it's the ones that implement an interface. So the machine down here, the machine adapter, implements the machine port or machine interface. So they are also called, originally they were called driving adapters, and that's the ones above the blue line here. And below that, that's the driven ones. So the ones that use an interface and the ones that implement an interface. As you can see, a port can have, or an interface can have, different implementations or different adapters. So the machine port, for example, will implement the real communication with the machine, say over CAN or Ethernet or Bluetooth. You will typically have a simulator which you can use during development, and you will have some kind of mock which you use during testing. The same goes for the database and the other and all the other adapters. So the important thing, and if you have to take one thing out of this talk, it is this point here, the last point. The important thing is that the code from inside the business logic must not leak out into the adapters and vice versa. So that is an absolute no-go. And I have seen business logic which happily references QML properties in the GUI. So it's completely the wrong way around. That goes always from the GUI into the business logic, never the other way around. Or you have business logic where people happily write SQL statements and to query the database. That is totally wrong. So that is exactly this point. So one adapter doesn't know anything of the other adapters. They always have to go through the business logic, and they can do so by signal slot connections. Yeah, that's the typical way in Qt actually. So that is the important point. There are clear interfaces, and the business logic doesn't know whether the machine uses CAN or Ethernet or just simulates or whatever. It shouldn't. It doesn't know, and it doesn't know whether you use an SQL database or whether you use an in-memory database or just a JSON file. That it shouldn't care about that, and that has a lot of good consequences. So, for example, if we look on our product over time, so how that develops. In our version 0, well, we have the GUI, of course, we have a database, and we have the machine, and our application talks to the machine over CAN or Git. You can get it out, release it, customer is happy. In version 1, well, we found out, the CAN bus doesn't have enough bandwidth. So we replaced the CAN bus by an Ethernet connection to get a much higher bandwidth. So it's just the only affected component is the machine adapter, and so we replace all the CAN bus code by Ethernet code and say get some MQTT messages instead of CAN messages. The rest of the application doesn't know about this change. For the rest of the application, the machine still looks exactly the same as before, as in version 0. Another thing we might add in version 1 is an updates component. So we extend our hexagon, our application, and extending it is always good. So that's always okay. So it follows the open-close principle, where you are open for extension, but you are closed actually for modification. And that's what you do here. You add a new interface, that's a clear extension, and you will have to add some functionality or some interfaces here in the GUI port, and maybe even, don't know, yeah, probably the GUI port only. So you're extending things, and that's okay. And in the version 2, you might add, say, remote diagnostic and support via VNC. Let's make that easy. And you might decide, okay, I don't want the message processing in the same process as my GUI application is running. I move that into a separate process, maybe so that multiple applications will see the CAN messages. So once you have multiple applications that need access to your machine messages, then you have to move that into your own process. And then the communication here is done via IPC, inter-process communication, with a separate process which does the message handling, the message processing. And again, the rest of the application, the business logic and the other adapters, don't see anything of it. And you can use this in for other configurations. So during development, you use a simulator probably. You don't necessarily have CAN adapters lying around and a machine standing in your office. That's typically too big. So you use a simulator. Or if you want to test the GUI in the system context, well, you write tests for the GUI and you use mocks for all the other adapters. And then you can, the business logic is the real thing, and then you can test your GUI in the system context. Same if you want to test your update component in the system context. So how do you, or how do we get a walking skeleton, a simple implementation of hexagonal architecture into place? Well, we choose one driving requirement, or an architecturally significant requirement. So, and the one I chose is the GUI shall show the current engine speed. Well, you know these dials in cars and harvesters and tractors and so on, which show the engine speed. So there is an engine ECU, an electronic control unit, which sends the engine speed in a CAN bus frame over CAN bus to our application, to our terminal. So that's communication over CAN bus in the vehicle, and then going to a different ECU, which is our terminal. So the machine sees the CAN frame and stores it in a twin of the real engine, and it transforms it converts it into a quantity. So the business logic must not know about CAN frames, so we have to lift the abstraction level and create a quantity. And the quantity is just a number, the 930, and a unit, which is the RPM in this case. So the business logic has a model, a main model in that case, which is the model for the view in the GUI. And well, you have to be able to access something like a quantity object in a QML GUI, you have to derive your quantity from a Q object. So that is a technicality you have to deal with when you go from C++, Qt C++ to the QML. So it derives from a Q object, so you have a quantity object. And then you can display the value and the unit in the GUI. So it's what the driver sees is 930 RPM. So the important things again is neither the GUI nor the business logic have any clue that the machine uses CAN messages or whatever messages. The business logic provides the C++ models for the QML GUI, and the GUI must not depend on the machine. So the GUI always goes through the business logic to get some information from the machine. So now I'm looking into each component. So we have a machine, we have a business logic, we have a GUI component, we have to create the hexagon in the main function. And I'll show you some code, and you can find the code on my GitHub repository. So we first have the machine port with a product adapter. So that would be the machine adapter we use in our real product. So it's nothing simulated, nothing mocked. That's the real thing. So we see that there's an engine ECU sends CAN frames, so socket CAN frames, over to our terminal, which uses Linux. That's why the terminal sees it as a socket CAN frame. And the QCAN bus device class reads these CAN frames, or it gets them from the Linux kernel and creates a QCAN bus frame from it. So that's the first lift of abstraction. Then it passes it on to a CAN bus router. So the CAN bus router does two things. First, it decodes the QCAN bus frame into a quantity. So it has to figure out that the third and fourth byte in this engine speed message is the engine speed, and there's other information encoded in it. So, and then transforms it into a quantity object, which is stored in the engine twin, and the business logic can actually access the engine twin and then the quantities through the machine. So there is a getter in the machine interface, which returns an engine twin. So that's the basic schema, the basic structure. And in code, it would look a little bit like this, or it looks like this. You create a QCAN bus device, and it's actually, you use socket CAN. There are other CAN variants which you could use, and you use the CAN0 network interface. And then you pass this, you inject this into your CAN bus router, which decodes the message and sends it to the engine. And this sending from the router to the engine is done by a signal slot connection. So a signal slot connection, it's very much like it's published subscriber. So if you know the published subscriber pattern, you know signals and slots. So the router here publishes this new engine quantities signal, and interested classes like the engine will connect to that. So they will subscribe to it with the update quantities slot. And that means, so whenever the router sees some messages coming in, some CAN frames coming in, it will collect a couple of them in a list and then send it to the engine twin, which will catch it in the update quantities slot or function. And that is actually the signal slots. Queued signal slots are an excellent means to decouple sender and publisher and subscriber. So it goes through an auto-generated mediator. So the router doesn't know anything about the engine and vice versa. The router only knows about a mediating object, and to which the engine also subscribes. And so the engine knows the mediator, the router knows the mediator, and this connection tells the mediator, oh, whenever you see a new engine quantities signal coming in from the router, well, please tell the engine twin and call the update quantities function. And that's auto-generated. The mediator is auto-generated in Qt. That is what the mock, the meter object compiler does, actually. Good. If we now say we don't have a real CAN bus, the CAN bus adapters are pretty expensive, so $250 for one. Not that cheap, actually. So you replace the actual ECU with a CAN bus simulator that just generates CAN messages. And then instead of the QCAN bus device, you use the mock CAN bus device, which derives from, which implements the QCAN bus abstract interface and does everything in the process, so it doesn't read anything from the Linux kernel and or from the real CAN bus. It just gets the messages, the Q CAN bus frames from our CAN bus simulator. You can actually use the CAN bus simulator to play back recorded CAN traces. So if you have a bug in the harvester, so on the field, then you record a CAN trace on the harvester, and then you play it back in the CAN bus simulator. So it's a very effective means to find problems in the CAN communication on your machine. Then it goes the normal path as before into the CAN bus router, the engine twin machine, and then finally into the business logic. Nothing changes there. And that's again the thing. So the business logic doesn't even notice that you are simulating the CAN bus now. In the code, the main change here is this connection where the simulator, whenever it has generated some fancy messages, emits a signal which is caught in this slot in the mock CAN bus device. The rest of the code is basically the same. You can take that a step further, so you can have a test adapter which uses just the mock CAN bus device, where you can actually observe messages going to the CAN bus, or you can control what messages come from the CAN bus. And controllability, observability is pretty important in testing. Again, so the business logic is now replaced by a machine test, so you can test your complete machine component with that. Pretty neat. You can, and I mentioned that already, you can say 3 years down the road, you have to replace CAN by Ethernet because of bandwidth problems. While you do that, you just replace your CAN bus device by a Q network interface, and then you have a MQTT router. Say you're using MQTT to send messages over Ethernet, and you get an QMQTT message, and from then on, the MQTT router decodes that in a quantity, and from that point on, it's the same. So again, the same. The business logic won't notice. Fantastic. How do you create the machine component? Well, I went for a very simple way of doing it. Just it's a global function actually, where you pass in your configuration, and it can be, say, a product, and then you create a product machine object. Or if it's the simulator, you create a simulator machine, and you can do the same for testing, for the mock, and so on. And you can create different adapters for different use cases. And you will use that in main as well. Good. Then it plays a role. So you can not only switch out the adapter, so say from CAN to MQTT or to a mock adapter or a simulator, you can also use the adapter pattern to change where your adapter is running, where it is deployed. So far everything was done in the main thread, which is obviously wrong to do. So you shouldn't do that. On a harvester, you have something like 1,200, 1,200 CAN messages flooding in per second. And you don't want 1,200 CAN messages hit the GUI. It will start stuttering and freezing and eventually crashing. So you better put your CAN bus routers into their own thread, and you do that for each CAN bus has its own thread, and then you connect that as before. It's connected to the engine twin or the ECU twins, and now it's a signal slot connection from one thread to another thread, and that means it's done asynchronously, and that's done automatically by Qt. So it's not the signal slot connection is not a direct function call anymore, but it creates an object of the quantity, puts that quantity object in the message queue of the engine twin of the main thread of the other thread, and yeah, that's fine, and then eventually it processes that in the main thread. So Qt takes that for you. You can go a step further, put your message processing into a process of its own, and use an inter-process communication mechanism like Qt Remote Objects for the communication. And again, it looks, for both processes here, it looks very much like a signal slot connection. The marshalling and demarshalling of the messages is done by Qt Remote Objects behind your back. Or you could take it even a step further and put that on the microcontroller, which is often available on modern SoCs, and use RPM-SG to communicate with your microprocessor. And that's shared memory in the end. And well, the thing is, the business logic won't notice that where your message processing is done, whether it's done on a microcontroller, in a separate process, or in a different thread. It won't notice. The business logic is pretty simple. It's sandwiched between machine and GUI. It sees an engine twin, and it will be connected to the main model. And the main model will be available through in QML through singletons. So business logic is a singleton and exported, made available in QML. And then you can access it as businesslogic.mainModel. So the business logic constructor gets a machine. So it's a dependency injection in a constructor. And then the model is created on demand and stored in a member variable. And then you have the signal slot connection between the engine, which you get via the machine interface. And the engine speed signal is connected to the set engine speed slot of the main model. And yeah, so it's always the same idea. So you pass on information from one basically from one layer to the other layer, or from one object to the other object with signals and slots. It decouples enormously. GUI component. Also pretty simple. Now we have a language switch. We are now in QML, and so we import the models with this statement, and that allows us to define a property main model, and then we use our singleton to retrieve the main model, and then we can, here in the text things, we show the value of our quantity object. So we now are working model.engineSpeed is a quantity object, and we take the value and show that in the GUI, and we show the unit, the RPM. I'm jumping over that a bit faster. GUI port with test adapter. Well, we could flip out the GUI with tests, so tests for main view, instead of having the GUI driving this, we have some test code driving that. So that allows us to test the GUI in system context with the real business logic, but with mocks for the machine object, maybe for the database object, and so on. And the mocks can be reused from the unit tests of the machine and the engine twin. So that was one of our configurations of the hexagon configurations we saw earlier. And the interesting thing here is Well, we create a machine object here. It's a shared pointer using our create machine function with the mock now, not with the product. It creates a business logic object where we pass in the machine. And then here in this case, we store for testing, we store the model in a member variable, and then we can start testing it. So we tell the machine to emit an engine speed here, the engine speed with 930 RPM, and then we can compare that actually in the next line. And so we can test that our terminal really displays the engine speed. And as we also have some GUI tests for our QML code, we have the whole thing covered. And the final thing is we have to create the hexagon. That is now easy because it's basically what we did in the GUI test. Nothing much different. And so we have in the main function, we create our machine with the create machine function. And now it's a product, obviously, not a mock anymore. No fakes anymore. Now it's the real thing. And we create the business logic, pass in the machine we just created. And then that is, well, that's the way to get the QML GUI up and running with the main.qml. And that would then show, at the moment, it just shows the 930 RPM. Actually, it counts it from, I think, from zero up to 3000 RPM and then starts over again and shows that. So, and that is, it is very simple, but our very simple use case showing the engine speed allowed us to create a walking skeleton of the hexagonal architecture. And what you hopefully have seen now is, well, there is some additional complexity. Yes, there always is if you use patterns, but it's pretty little. So the positive things here is high testability. It's actually more or less ingrained in the architecture that it's easily testable. It's highly modular, so different teams can work on different adapters and on different adapters. You can split your teams according to the adapters you have and to the business logic. If you want to do that, I would prefer to have well, one team doing everything, so the vertical slice. But it's possible, and you can easily modify, so you can extend it thanks to the interfaces you are using. Use the open-close principle, extend your interfaces, don't modify them. Then you're breaking the modularity. And it should be fairly easy to maintain and find bugs. So what I hope is that I could make my case that the hexagonal architecture should be the standard architecture for Qt embedded HMIs, and it's definitely a successful architecture. So it delivers value to the customers. Here are the resources I used for the talk. You find the source code down here, and I will improve it over time pretty quickly, so you will see more functionality. Now it's time to say thank you. Here's my email. If you have questions, feel free to ask me. I have a website where you will see similar posts about hexagonal architecture and other stuff about Qt embedded systems. And I write a monthly newsletter if you're interested. So thanks a lot. It was a pleasure giving this talk.
Thank you for the talk.
And I'm open for questions.
I liked it very much.
Good. And you're right, Jens, with the might want to use make shared. There.
Yes, that's of course. But I know it's like demo code on a slide, so I might not have that there.
Yeah, you do not have infinite space there.
Yes, true. So, yeah, if you have any questions, you can post them either to the Q&A tab, which I don't see any questions in, or to the chat. And I right now don't have any question, but I find your approach interesting to basically use the signal slot methods to communicate between boundaries, and then to also kind of use this to plug in different models and mocks as that.
Yeah, that is one. That's, I think, the beauty and strength of signals and slots. It decouples the two objects talking to each other.
So,
well, you have some overhead, obviously, but normally that isn't a problem. And
the only question which directly comes to my mind is what do you use as an interface? How do you use that if you can't use Qt on the other side of the code?
Well, then it's typically if you can't use signal slots. Well, I think Boost has signal slots as well by now, and
they do. They have two. They have signal slots libraries.
Exactly. So you could use that as a pure C++ implementation of it. And the other way is typically then you would use a dependency instruction in the constructor. So you have to, like you saw it for the business logic, where the machine is passed in, and then the models in the business logic could call functions on the machine.
You would use a strategy pattern and drop that in, and then have that connect.
Exactly.
I think there's a question in the chat.
Yeah. What is the major difference to MVC or MVVM model view model? The model view controller pattern is only used in the GUI part, I think. So it is. If you and it is actually used here. So you saw the main model, you saw the QML view. That's a model view that uses the model view pattern. But the rest, all the other adapters don't use model view. But the idea is obviously similar. So it's but I wouldn't call the whole thing a model view controller pattern. That is just a pattern on a much smaller scale. So we are now talking about the whole an architecture for the whole application. But there are elements. Even the 3 layers architecture is actually pretty similar. If you have the if you have this hexagon, you see the 3 layers. If you go from the GUI through the business logic to the machine, so that's a clear 3-layer architecture. Then you can unfold GUI, business logic, and database. So that's another 3-layer path, or updates, business logic, database. So you can unfold your hexagon in the 3 layers architecture, and then you're coming close to model view controller or the presentation abstraction controller, the pack pattern also. So if you're looking at 3-layer architecture, you're getting closer and closer to model view controller. So I can see your question, or how that flows into the hexagon. The hexagonal architecture is a generalization of the 3-layer architecture, understanding that it's not just 3 layers, but each layer, or the bottom layer of the 3-layer architecture, would have typically different components, different libraries. Here it would be the database and the machine library, and that isn't really reflected in the 3-layer architecture. So, and when you move it around in the hexagon, then you have two clearly separated components. So it makes things a little bit clearer, I think.
Yeah, I think you're not limited to one hexagon. You could like have
forget the hexagon. Here it's just 4, it may be 3. You may find 7 adapters or maybe 8, but that's a lot. So 6 is a good number.
The other thing what I found interesting, like when you talked about sender receiver like that, or like, signal slot, that this is so close to what the standard is trying to do with sender receiver now, just in a way more high level way than what Qt already has.
Yeah.
And on the other hand, I see we are going a bit over time, and I think I want to thank you for the talk. Really, really nice overview. Great content. Thank you so much for that. And I'm going to take us now on the break, and then we're going to have the next session in a few minutes at 3 o'clock.
Thank you very much. See you in the lounge.
Okay.